All right, so we are going to talk about a proof method called proof by contradiction. All right, and so this is essentially trying to prove that a theorem is true, but going about it through the back door. All right, so we're going to have some definitions first and then talk about what this proof method actually is. So first, a tautology is a statement that is always true. All right, and of course that's going to have the opposite one. A contradiction is a statement that's always false. All right, so if we have a statement that is absolutely always false, we call that a contradiction. The most classic contradiction is, okay, so if A is a statement, A and not A is a contradiction. All right, because you can't have a statement be both true and false at the same time. All right, so if A is true, not A is false. All right, and so you can't have both true and false at the same time. All right. Next, we're going to need a theorem about implications. So, if-then statements can be written in shorthand like that. All right, A implies B. That's the same thing as if A, then B. The vast majority of our theorems are written that way. So, this statement is logically equivalent to not A or B. Okay, you can prove this with truth tables pretty easily. Okay, so why do we care about that? Because we're going to want to negate, when we start doing contradictions, we're going to want to negate our if-then statements. We're going to figure out what is the negation of the if-then statement. So what is the negation of A implies B? Well, if A implies B is the same thing as this or statement over here, well, we know how to negate or statements. We can use De Morgan's law. So the negation of if A, then B is going to be A and not B. All right, and if we think about this, this kind of makes some sense because if A, then B, all right, that's saying if A is true, then that implies that B is true. All right, the negation of that is going to be A being true, but B being not true. And that's exactly what A and not B is saying. A is true and B is false. All right, so this gives us everything we need to talk about a proof by contradiction. So for a proof by contradiction, what we're going to do, all right, I'm going to explain this, then we're going to look at some examples. What we're going to do is actually assume that the theorem we're trying to prove is not true, right? That it is false. All right, and this is why we're going to need the negation of an if-then statement, because we're going to have to assume that A implies B is false, so that means assuming that not A implies B is true. We're going to assume the negation of our theorem. And so by assuming that our theorem is in fact false, we're going to take that assumption and see where it leads us and try and show that it leads us to a contradiction. It leads us to some place that is always false. And therefore, if our assumption that the theorem is false leads to a statement that is absolutely always false, well, that's not good, all right? So that means that our original assumption had to be wrong in the first place, and therefore our theorem has to be true. So we're not really working directly with our theorem to prove that the conclusion is true. What we're doing instead is making this assumption that the theorem is false and proving that, well, that leads to some bad place. That leads to a contradiction. Therefore, our original assumption had to be wrong and our theorem has to be true. All right, so let's take a look at an example. We have the theorem that the sum of two even numbers is even. I'm not sure if we ever actually proved that, but I think you'll believe me on that one pretty quickly. Oops. So the sum of evens is even. Okay, so let's try and prove this by contradiction. So the first thing we're going to do, maybe there's some initial stuff. So, okay, fine. Let's do some initial stuff. Let n and m be even integers. All right, so the first thing we're going to do is we're going to assume that our theorem is false. All right, so suppose, for the sake of contradiction, all right, so we're telling our reader that we're doing things by contradiction. Otherwise, the reader is going to get very confused as to why you're assuming this thing you're trying to prove is false. All right, so we're letting our reader know. Suppose, for the sake of doing a proof by contradiction, that n plus m is odd. All right, so we're going to make this assumption right here. Okay. And now what we need to do is go through and use the two bits of information that we have. N and m are even, and n plus m is odd, and somehow get ourselves down to a contradiction. Okay? Now, this is actually a very bad way to prove this, and I'm going to show you as I work through this. But the way that we're going to get to our contradiction is really by just doing the direct proof. And so this is sort of useless. We're going through more work than necessary, but it's a good way of explaining kind of how you do a proof by contradiction. So since n and m are even, we know that we can write n as 2k and m as 2l. All right, I'm doing bad writing now because I'm just trying to write quickly. And so n plus m is 2k plus 2l, which is 2 times k plus l, which tells us that n plus m is even. All right? And now that leads us to our contradiction, because we have shown that n plus m is even and n plus m is odd. So we say explicitly what the contradiction is. This is a contradiction because a number can't be both even and odd. And we have shown, starting with our assumption that the theorem is false, that n plus m is even and it is odd. All right, so that is a contradiction. Therefore, the original theorem must be true. Okay, so then your final statement is, okay, therefore, since I've gotten to a contradiction, my original theorem must be true. All right, or n plus m must be even, or some way of stating that. All right, so you start off assuming the negation of your theorem and show that that leads to some contradiction. All right, let's do one more example, which is again going to be a bad example. This is not the type of proof that you do contradiction for, because it's really just adding extra words, but it does a good job of showing how to do this. So if 6 divides n, then 3 divides n. All right. So first, let n be an integer such that 6 divides n. Suppose, for the sake of contradiction, that 3 does not divide n. All right. So so we have our assumption that 6 divides n, and we have this extra assumption, for the sake of contradiction, that 3 does not divide n. All right, well, 6 divides n, that implies that n is equal to 6k, which is equal to 3 times 2k. All right, which through a little bit more work, again, I'm writing poorly here so I can do things quicker. This tells me that 3 divides n. Now, I explicitly state the contradiction. This is a contradiction because, you could say this a bunch of ways, but you could say because we assumed 3 does not divide n. Therefore, theorem must be true. All right, and there's better ways of writing that, and we can talk about those when you present. All right, I'm just kind of writing quickly to get the idea across here. All right, so this is, let's look at the building blocks of this. All right, we have the initial building blocks that would normally do for our proofs. And then we have, for a contradiction proof, suppose for the sake of contradiction, the negation. All right, so you're assuming the theorem is wrong. Then you go through and do work, some work, in order to lead yourself to a contradiction, and then you explicitly state what the contradiction is. That's important. You can't just lead yourself somewhere and then assume the reader sees the contradiction, because sometimes it's not obvious. So you have to explicitly show the reader what your contradiction is. And then you say, therefore, the theorem has to be true. All right, we did the same thing back here. We suppose, for the sake of contradiction, the negation of our theorem. All right, that n plus m was odd. We do some work that leads to a contradiction, and then we state what the contradiction is. You can't have a number be both even and odd. All right, and then therefore, the theorem has to be true. So, some good points and bad points about contradiction. Good point, you get to use more information. All right, for this theorem, when you prove it directly, the only piece of information you're allowed to assume is that 6 divides n. And then somehow you need to use that information to show that 3 divides n. All right, that's how you did it the first time. When you do a proof by contradiction, you get to assume that 6 divides n, and you get to assume that 3 does not divide n. That's more information that you get to have at the beginning. All right? Same thing over here. At this one, you really have 0 information to start off with, except that n and m are even, if you're proving it directly. But if you prove it by contradiction, you also get to assume that n plus m is odd. So you have more information about these integers that you can use. All right, so you get to use more information. So proof by contradiction can be very nice in that way because you have more data about your variables that you can use. Bad point. You don't know where you're going. You don't know what the end of your proof is. When you are proving this theorem right here, you know that you're trying to prove that 3 divides n. All right, that is your goal. So you could work a proof from the top and from the bottom. Start at 3 divides n and see, okay, where do I need to get to so that 3 divides n? And so you know your goal. You know what you're trying to show. When you do a proof by contradiction, all you know is you're trying to get to a contradiction. What that contradiction is, you don't know when you're starting out. And so you get to use more information at the beginning, but you don't know exactly where you're aiming at. You just know that you're trying to find some contradiction somewhere. All right, so there are good points and there are bad points to a proof by contradiction. There are times where it's definitely the way to go. So there are times when it's the only way to go. There are times when a direct proof is certainly better and certainly creates a cleaner proof. And there are times when it kind of doesn't matter one way or the other, and both have their benefits. All right, so we'll talk about all of these as we do our presentations.